So I'm a fourth year undergrad at Delaware State University, and my project was with Princeton University and NAC, of course. I work with Juan Hermo and Dan Tamayo to find new irregular satellites and moons around Jupiter. Okay, so what are irregular satellites? We know them as moons today. So all of our four giant planets in our solar system possess these irregular satellites, but there is one difference of what a regular satellite is and what an irregular satellite is. So this picture right here is what regular satellites do. They're fixed circular orbits that are joined with the host planet. So they're usually fixed, while irregular satellites are just small bodies or asteroids that are floating around or are captured by the sphere of gravitational influence by these host planets. So on this right, bottom right, you can see the orbits are not fixed. They're wild, crazy. They have different orbits at different days. So the velocity and their timings are all different, which are characterized by large, highly eccentric, or highly inclined orbits, as you can see on the right. So why is this important? Our solar system is always evolving, and we always want to know what's in it. And the main focus is we believe that these planets are moving around in the early solar system time, and with all these small bodies and asteroids just floating around and being captured by these planets, that we believe like we can, I guess, be like a tracer of how the movement of our solar system was billions of years ago. So that's the main reason why we think this is important, because of the capturing of these small bodies at random points. So it's kind of like a tracer of how our solar system came to be, of what it is today. So with my partners, the goal of my research was to find new irregular satellites by using the Pan-STARRS survey telescope located in Hawaii. It takes a bunch of sky map pictures. We want to sort through them sort through them to see what's a star and what's a potential candidate for a regular satellite. So we use Python and Jupyter Notebook. So we try to make a pipeline code to eliminate the difference on which is which by the movement of Jupiter in the different images. So we create a pipeline, and then we wanted to create fake regular satellites so we can test out if our pipeline is even correct or if we're way off. Okay, the basics of my project. So these are two different images. The date is January 5th, 2011. So back in the day, to find these regular satellites, they would just stare, let's say image one for a while, and then stare image two and see which one moved. Obviously, to naked eye, it's almost impossible. You can't really see much. So our goal was to make a pipeline that could distinguish which is a star and which is a potential satellite just from like images like this. So the survey we used, the Pan-STARRS telescope, it's has 64 chips in it. As you can see, it's not 100% accurate because, as you can see, there's all these chunks missing, and we don't know if it's a defect or data missing. So we're not taking this data 100%. We taking in consideration of all the missing chips defects. And so the picture on the right, the X is Jupiter, and they say that Jupiter's hill sphere is the dotted line circle, so the outside, the bigger one. And that's the gravitational pull that pulls all these asteroids and little just small bodies that are floating around. And as you can see, the solid line is half the hill sphere. It's known that most of the irregular satellites that are found to this day are located in there because that's where the pull and gravitational force is strong enough to keep it instead of letting it just float away and these small bodies not surviving. So our chip is like in between half and half. So on this next plot I'm about to show you, it's going to show that most of these are actually closer into the Jupiter. So these are just a bunch of irregular satellites known to man, irregular satellites that we know today. And you can see they're all closer to Jupiter because that's where the attraction is strongest. Once it gets past maybe halfway out, a lot of them are just going to die and another host planet would just capture them. Okay, so this is a plot to show what we did exactly. So this is the first image would be the blue, and the second image would be the red. And this is Jupiter, the axis. And obviously it's a sky map that was taken. And the way we classified as what's a potential satellite, a regular satellite, and what's a star is by the distance. So as these small bodies are orbiting with Jupiter, they should move the same distance and the same direction as Jupiter when it moves. So if we've seen a difference that's so small or not anywhere near the direction or distance that Jupiter moved, we would just classify as a star. So let's say this black dot right here. That's Jupiter in the first image, that's Jupiter in the second image. That we can classify as a potential candidate. But all these little differences, like we just said, screw it, it's a star. We're not gonna even worry about it. So some of our findings that we found. So we created a pipeline, took forever, but we created a pipeline and we just plotted about 9 just random fake irregular satellites. And then we wanted to see if our pipeline could recover them, and sure did. But we also found something else. We found more irregular satellites. So these X's are potential candidates. Some honestly could be false detections. We're not sure with the data we have because we didn't go through all of it. And the telescope wasn't 100% credible, but we found one that was actually a known irregular satellite. It's pretty known. It's Himalaya. It's probably one of the biggest ones that we know around Jupiter. That's the R in deck of it. So looking at this, we can see our pipeline was successful. Maybe with better data, we'll have more success, but there's just some more investigations we have to do. Like if we had more time, we can go through more. So this is just the indices that we get through our code. And the first one is Himalaya, which I think is right here. I think it's the one, yeah, I think it's that one. But as you can see, our data is not 100% because we have 3 indices out of 4 that are needed. And that could also still be from the detector with the defects. We're not sure. We didn't really go through it. We just used the ones that we could find. And as you can see, there's like 4 here. We have 4 and we have 4 that have landed in our chips. The conclusion, so we built a pipeline to automatically detect satellites from a large number of files of images. And then we tested them with fake irregular satellites, and we tested we can recover them from our pipeline. And we did end up recovering more than what we wanted. This research project was actually really big for more of the future than now. They said in a couple of years, the Vera Rubin telescope will be coming out, and it's known to take thousands and thousands of images. And using a pipeline like this could be like a prototype because they're expected to find hundreds of more irregular satellites, but we obviously need clear data and a better pipeline to kind of just sort through different chains of images. Any questions?
Awesome. Thanks, Fahim. Yeah, do we have any questions?
Hi, Fahim. Great. It was wonderful. I learned so much. One thing though I wanted to know is how did you go about creating the fake irregular satellites? Was there already a code that you used and changed input parameters, or did you actually like write a code to, you know, describe them?
We wrote a code. We just we kind of use the movement of Jupiter and kind of base it off that. So like if Jupiter moves a certain amount, we try to say like we plotted one fake irregular satellite and we want to like use Jupiter's distance and direction to create another fake irregular satellite. That was in the same parameters though. But we started the code, it was just like we based it off Jupiter's movement in the images.
Yeah, Fahim, great talk. I was curious about kind of the future that you mentioned of possibly applying a pipeline like this to Rubin observations. Would Rubin be capable of detecting even lower mass satellites? That is, it would find objects that would be out of reach of pan-stars?
I think so. I think it's more it'll be clear images. Like we can actually see more instead of the pan-STARRS, which is kind of old. It's like it's not giving us clear data as we would like.
Okay.
For these satellites, the irregular satellites, are they different from like the 80-ish known satellites that Jupiter has? Or does that include these irregular? Like, are they distinct population?
The 80 that are known-ish, those are the ones that like I guess formed with Jupiter. These are just ones that like have been floating around years and years ago that are just captured by the gravitational pull of Jupiter.
Okay, so they're irregular because they're like more recently caught?
Yeah.
Cool. Okay, thank you.